Today we are going to be talking about resolution. Before we can understand resolution, we must first revisit what we know about diffraction. We learned that when a light is incident on a single slit, there is a pattern of constructive and destructive interference that can be seen by the bright fringes and dark bands on the screen. Where these maxima and minima form is dependent on the angle theta. We know that the angle theta is equal to lambda divided by b, where lambda is the wavelength of the waves and b is the slit width. Now let's look at a different situation where there are two source points. As the light enters through a circular aperture, which is new for us, there will be an intensity distribution graph for either of the sources. If the central maxima of both the light sources are far enough apart, then we will be able to distinguish the two different sources. In this figure, you can see the distinct central maxima. Here is what this would look like on the detector screen. Here you see two central maximas, and they are distinct and they are separate, and we can see them both. If the central maxima had more overlap, then you notice that it becomes more difficult to distinguish the two separate central maxima. If the central maxima are experiencing even more overlap, then it becomes even more difficult to distinguish the two separate central maxima. Let's begin taking some TNOTES. Resolution is the ability of an imaging system to produce two separate images. We sometimes say the sharpness of an image is the level of resolution a device has. Some examples of imaging systems are the eye, a camera, or a radio telescope. If light waves pass through, so here we have our light sources, if light waves pass through a single circular aperture, the angle theta is equal to lambda divided by b, where b is the diameter of the circular aperture or lens or mirror producing image. The equation here that you see is adjusted by a factor of 1.22, and this is for circular apertures. And that gives us an equation of theta equaling 1.22 lambda divided by b. You do not have to know how 1.22 was derived. Notice that the angle is proportional to the wavelength and inversely proportional to the slit width. All right, let's make sure we get this equation into your notes. One thing to note is that the angle here, theta, the smaller the angle, the higher the resolution. There is a limit to which two objects can be distinguishable, and this is called Rayleigh's criterion. Rayleigh's criterion states that the limit of resolvability is when the middle of the central maximum of one diffraction pattern coincides with the first minimum of the second pattern. So here is the middle of the central maximum of the first diffraction pattern, and here is the minimum of the second pattern. If we go beyond this point, we will be unable to view the two separate maxima, and we call this as being unresolved. There are factors that affect resolution. Use the known equations that theta equals s divided by d equals 1.22 lambda divided by b to mathematically prove the following factors. One factor that affects resolution is the wavelength. If the wavelength is shorter, this creates higher resolution. A second factor is how close the objects are to each other. The smaller the distance between the objects, the higher the resolution. A third factor is how far the objects are from the observer. If the distance between the objects and the observer increase, then the resolution will be higher. The last factor is the size of the aperture, and this is known as the variable b. We can achieve higher resolution if we use a larger aperture, and this is why big lenses are used when you're looking at cameras or telescopes. Let's look at some real-life applications of resolution. CDs and DVDs use reflection from laser lights that shine on areas called pits, which are grooves in the surface of the CD or the DVD. There are circular tracks that are placed around the disc. The width of these tracks are around 5 times 10 to the negative 7th meter, or 500 nanometers. The wavelength of the laser that is used to read the information is 780 nanometers, which has a limit of resolvability. To increase the amount of data the disc can hold, you would need to make the tracks closer together. However, you would also need to decrease the angle of resolution. How we can achieve this is by decreasing the wavelength of the laser. For example, DVDs use a laser that has a wavelength of about 650 nanometers. Blu-ray DVDs use a laser with a wavelength of 405 nanometers, which correlates with the blue color of the visible spectrum. So by making the tracks closer together, we're able to fit more information onto a disc. And then by using a laser that has a lower wavelength, we are able to read the disc. Radio telescopes can be very large in diameter. The world's largest filled aperture telescope, or full dish, is the Arecibo radio telescope located in Arecibo, Puerto Rico, whose 305 meters dish is fixed into the ground. The diameter of the dish B is the size of the aperture. When viewing objects out in space, the wavelength depends on the object being observed. Looking at the equation, theta equals 1.22 lambda divided by b, the larger the size of the aperture, the smaller the angular separation, or theta. A scanning electron microscope is another very useful tool we can use in order to magnify solid objects by scanning it with a beam of electrons. Here is a diagram of what compartments exist inside of the scanning electron microscope. This device can resolve 2 points that are 0.1 nanometers apart, which is about the size of an atom. Compare that with a standard classroom light microscope that can resolve 2 points that are at least 200 nanometers apart. And this is why we're able to see such a higher resolution using the scanning electron microscope versus the classroom microscope. Here is a comparison of a specimen under a light microscope versus the scanning electron microscope. Over on the left, we have the light microscope of something called a radiolarian. And over on the right, we have much better resolution. You can see so much more detail. And this is because the spacing between the two parts are able to be resolved with a scanning microscope versus that of just the light microscope in the classroom. Notice how much sharper the images are when the distance between the 2 points is smaller, therefore making the angular resolution smaller. Here are 2 more pictures for you to look at that shows the level of resolution of looking at a fly here under the scanning electron microscope, and over here on the right, these are pollen grains. Here you can see from Earth what 2 stars look like depending on the resolution of the imaging device. Over on the right, we can distinguish 2 separate stars. As we move more to the left, we reach past the limit of resolvability. Here we see 2 stars, and their light is heading towards Earth. We know that the angle theta, also known as the angular separation of the 2 objects, is equal to s divided by d. However, if viewed through a circular imaging system such as a telescope, we know that theta equals 1.22 lambda divided by b. We can then equal s divided by d to 1.22 lambda divided by b, depending on what we need to solve for. Here's an example. The camera of a spy satellite orbiting 200 kilometers above the Earth's surface has a diameter of 35 centimeters. What is the smallest distance the camera can resolve on the surface of the Earth, assuming that the wavelength is 500 nanometers? Go ahead and try this and then start the video back up. We know that the distance is 200 kilometers, which is equivalent to 2 times 10 to the 5th meters. We also know that B, which is the size of the aperture, is 35 centimeters or 0.35 meters. And we also were given that the wavelength is 500 nanometers, which is 5 times 10 to the negative 7 meters. The angular separation equals s divided by d equals 1.22 lambda divided by b. We are going to solve for s because we're looking for the distance the camera can resolve on the surface of the Earth. When we solve for s, we get s equals 1.22 times d times lambda divided by b. Plugging in all of our numbers, we get an answer of 0.34 meters. Here's another example. We have the headlights of a car that are 2 meters apart. The pupil of the human eye has a diameter of 2 millimeters. Supposing the wavelength of light is 500 nanometers, what is the maximum distance at which 2 headlights are seen as distinct 2 separate objects? Go ahead and try this and then start the video back up. We know that the distance equals 2 meters, and this is the distance between the two lights. We also know that B equals 2 millimeters, which is 2 times 10 to the negative 3. We are also given the wavelength at being 5 times 10 to the negative 7 meters. We are given our equation for angular separation. We solve for D and plug everything in, and we get an answer of 7,000 meters. We can resolve diffraction gratings mathematically with the following equation. R equals lambda divided by delta lambda equals m times n. R is the resolvance, delta lambda is the smallest difference in the wavelength that can be resolved, n is the total number of slits that are illuminated, m is the order of the diffraction. The higher the R, the higher the resolution. Here is an example that asks you to find the resolving power of the diffraction grating for two light sources of wavelengths that are similar, however a little bit different. So we have one wavelength of 589.00 nanometers, and we have the second wavelength of another source of 589.59 nanometers. We are also given the width of the entire grating is 1.2 centimeters, and we know that the number of lines is 600 lines. Because we know Raleigh's criterion states that the only way we can distinguish the two central maxima and images is if the first maximum coincides with the minimum of the second pattern. This would be the minimum separation distance. If the central maxima were further apart, we would continue to have resolution. So, the resolving power R must be greater than the average of the two of the lights over here, divided by the difference in the wavelengths, delta lambda. The first step would be to calculate the number of slits. We know that we have 600 lines per centimeter and that there is a width of the entire grating as being 1.2 centimeters. When we multiply that, we get 720 lines or 720 slits. Step 2 would be to solve for R. Now, the resolving power equation has two parts. We know that R can equal lambda divided by delta lambda, and we also know that R can equal m times n. So we're going to solve for each part of this and then compare the answers. For the first part, where R equals m times n, we get an answer of 720. For the second portion of R, we have our first lambda here, which is going to be the average of the two lights, and that will be 589.00 plus 589.59 divided by 2, and then that is going to be over the difference of the two wavelengths. When we calculate that, we get an answer of 999. Then we compare this 999 with the 720 from the first calculation. The wavelengths of 589.00 and 589.59 require a resolution of at least 999. Our diffraction grating gives a resolution of only 720. Therefore, we will not be able to resolve the two lines in the first order. If we were to figure out the second order of maxima, we would multiply 720 lines by 2, and we would get an answer of 1440. Because the wavelengths require a resolution of at least 999, we would be able to see the lines resolved in the second order maxima. Okay, here are 3 practice problems for you to do. Number 1 is just one problem, number 2 has 2 parts, and number 3 is located right here. Be ready to have both of these items, the TNOTES and the questions, stamped, and thank you very much for watching.